So next up, let's discuss gluconeogenesis and its irreversible enzymes. So what does the name gluconeogenesis mean? It simply means making new glucose. Gluconeogenesis, which is shown here, is basically glycolysis in reverse. Now gluconeogenesis takes place primarily in the liver, so when the body is low on blood sugar, the liver uses gluconeogenesis to pump out more usable glucose. In this way, the body will maintain a euglycemic state, even during fasting. So can you think of a few other places where gluconeogenesis is performed? There you go, that'd be the kidney as well as the intestinal epithelium. Now this process will begin with pyruvate, as you can see here, and it ends with glucose and uses most of the same enzymes as glycolysis. However, in this process, there are 3 irreversible steps during glycolysis, and the body uses 4 unique enzymes to bypass these 3 irreversible steps. Now before we look at these 4 enzymes, do you happen to remember the cofactor required for carboxylase enzymes? There you go, hopefully you were thinking about biotin. And the first key enzyme of gluconeogenesis is pyruvate carboxylase, which converts pyruvate to oxaloacetate. Now this reaction occurs in the mitochondria and it requires biotin as well as ATP. And it's activated when there's high concentrations of acetyl-CoA, since this means you don't need to be making more acetyl-CoA. And in our next step here, phosphoenolpyruvate carboxykinase converts oxaloacetate to phosphoenolpyruvate, or PEP, within the cytosol of the cell. And you can see this here. And this step uses GTP as a source of phosphate. Now for our next step in gluconeogenesis, fructose 1,6-bisphosphatase, which is the third irreversible enzyme here, converts fructose 1,6-bisphosphate to fructose 6-phosphate. And for our final step here, glucose 6-phosphatase removes a phosphate from glucose 6-phosphate to form glucose, which is then free to be released into the bloodstream for the body to use. So just to review that process one more time, pyruvate is converted to oxaloacetate by pyruvate carboxylase, and this reaction requires biotin. Next up, oxaloacetate is converted to phosphoenolpyruvate by phosphoenolpyruvate carboxykinase, and this step again requires GTP as the phosphate donor. Then next up, we have fructose 1,6-bisphosphate, which is converted to fructose 6-phosphate by fructose 1,6-bisphosphatase. And our last step here, glucose 6-phosphate, is converted to glucose by glucose 6-phosphatase. Now in this last step, this mainly occurs in the hepatic endoplasmic reticulum, and it doesn't actually take place in muscle, since muscles actually lack this enzyme. And glucose 6-phosphatase is also the enzyme that's mutated in von Gerke's disease, which is one of the glycogen storage diseases that we'll talk about later. So in summary, gluconeogenesis occurs primarily in the liver, and it creates glucose from fatty acids or from TCA cycle intermediates. And it should come at no surprise that a deficiency in one of these 4 gluconeogenic enzymes can cause some hypoglycemia. Now on test day, how are you going to remember these irreversible enzymes of gluconeogenesis? Well, just remember that gluconeogenesis is the pathway that produces fresh glucose, where the first P here in pathway stands for pyruvate carboxylase. And the second P in produces stands for phosphoenolpyruvate carboxykinase. And our F in fresh stands for fructose 1,6-bisphosphatase. And our G in glucose stands for glucose 6-phosphatase. Now with all that said, is there any other way we can actually make glucose molecules? Well, here we see our TCA cycle, and odd chain fatty acids can serve as glucose sources since they yield propionyl-CoA, which can enter the TCA cycle as succinyl-CoA, as you see here. Now this is in contrast to even chain fatty acids, which cannot be used as a glucose source since they can only be broken down into acetyl-CoA and then disappears as CO2 by the time it reaches oxaloacetate. Well, alright, that's going to wrap up gluconeogenesis and the irreversible enzymes. See you in the next video.